Okay, just checking. All right, now I'm recording, so welcome back, everybody. I uploaded grades this morning, so you should be able to see how you did on homework 2 if you finished it. Not everybody has finished it. Not everybody has started, to be fair. So I will not be talking about it in class much, but if you look at an answer and you're not sure why it's wrong or you'd like some clarification, I'm happy to speak with each of you individually about your answers. The next thing you'll have to do will be a formative assessment, and that is not ready yet because I wanted to see how far we got today before I put it up, but I will let you know when that's ready, as well as your next homework, which will be about the thing we're doing today. So homework 3 will be about example 2B, and I am learning through trial and error with the homework system what things work in R the same way that they work in SAS and Stata, and what things don't. So if any of you had issues using R with respect to the walled tests, I got a couple emails from folks who said their answers were off by like 100th, and so it was just enough to count it as incorrect in the homework system. If you missed any questions because of that type of rounding error issue across programs, please let me know, and I'll happily give you your points back. The way that the homework system works is that everything is run through SAS. Like, it's built through SAS, all the models, all the answers, and so then I take one of the data sets and I see if I can generate the exact correct answers in Stata and in R. And if I can't, then I change the question or do something to make it so that I can. But in this case, it looked on my end like everything should have matched. And lo and behold, it didn't, for reasons that I still don't know. So I apologize for anyone who was frustrated by that, but I'm learning what things I can't ask. So there will be no walled tests in the next homework. There's just not going to be any. So,
because I was talking to some people last night on it, I think it's a rounding issue. And I think like if you round once and then you use that estimate and then round again, then it ends up getting off by like a tenth or 100th of a point or something, or like more than the error that's included in the homework.
Yeah, the wall test shouldn't have any rounding error because they're taken from the model results directly. So I didn't input any hard-coded values. I just had it do the chi-square analysis. I don't know why it's off just a tiny bit sometimes. I know that in example 2B it's off for more than that because the standard errors are off, and so we'll talk about that today. But yeah, Solomon says you kept guessing until you got the right answer. That's never a bad strategy. Just like go up or down by a 100th of a point or a 10th of a point, and it may take it. But yeah, let me know if that happens though, because that's not cool. I did not intend for that to happen, but we're learning something new every day. So anything else about software homework that you want to talk about, that we can talk about, I should say?
Hey, I have a general question, like a conceptual question. So if you have main effect coefficients that are very not significant,
okay.
And then, but then maybe run a test for a simple slope, and then all of a sudden it becomes very significant according to p-values. Why is that the case?
Does the model have an interaction term in it that you're talking about?
Yes.
So the main effect that is given by the model output is specifically to the interacting variables being 0, whereas each of the simple slopes is evaluated conditionally on other values besides 0. So the nature of the interaction term means that the main effect must change as a function of the moderator variables, and so it could become, basically, because it's a linear system, there is a range of moderator values in which a slope would be significantly negative, a range in which it would be non-significant, and a range after that at which it would switch to being significantly positive. That is true of all slopes within interaction terms that are done with this sort of linear type of model. The only question is, what are the values of the moderator, and do they exist in your data in each of those ranges? Okay. Other questions?
Lisa, I have a question.
Hit me.
I asked a few about this, why we might use fake people, and they had indicated for graphs, but I don't know if you could speak to any other instances where you might use fake people. I realize we didn't have to do that for the homework, but curious on applications of, because I found myself lost in kind of understanding where we would apply fake people.
So fake people are necessary. So by fake people, just to clarify, I'm talking about adding cases to a data set that have values of the predictors that you're interested in, like prototypical values of low, medium, high, but they do not have values of the outcome. So by adding them to the data, you don't screw anything up, you're just adding cases. The reason you would do that is to get predicted outcomes quickly and efficiently without having to write out like an individual estimate statement for every single prediction, and without having to change the values and the terms in that individual estimate statement. So for instance, if I'm fitting models that have main effects only and I want to get predicted outcomes, I can change the model to have an interaction term and I'll still get predicted outcomes that are correct if the model is doing the predicting. Whereas if I'm writing the syntax manually, I have to change all of the values to make it correct every time I change the model. So in SAS, I do fake people because there's not an easy way to ask it to make predictions over a range of values in the procedures, or at least I've looked for it and haven't found it. Whereas in Stata, there's a margins command that allows you to easily say, I want a range over this level of this covariate and these levels of this covariate, and it's one statement that gives you a whole bunch of possibilities. In R, I didn't know how to do that at first, and so I did it the manual way, but then I did some Googling and found a prediction routine within a package called margins that works like margins. And then I also came across the predict function that you can use in the context of linear models that does a similar sort of thing.
Okay.
So I would say that fake people are needed if you can't figure out an easier way to get predicted values using some kind of built-in routine.
Okay, gotcha. Yeah, I saw an example, and I was like, do I? Doesn't this function handle that? So,
Yeah.
I appreciate that clarification.
And I think so part of what you're seeing with my syntax is literally me learning how to do things as we go along. So I started out with example 2, and I put the fake people in because that was all I knew how to do when I started. And then at some point I found the margins thing, and the fake people are not needed. And then I found the predict thing, and then the fake people were not needed. And then so it's a work in progress.
No worries at all.
I keep it real. You guys are getting the blow-by-blow of me trying to get along with R, and sometimes failing and sometimes succeeding. It's like that expression, why do you hit your head on the wall? It's like, because it feels so good when I stop. That's what I feel like, just banging my head against R, and then eventually something works, and it's like, oh my God, I win. So it's a work in progress. And there's more of that to come, by the way. A highlight that you'll get on Thursday is that I discovered that something that I had done consistently 2 years ago when I built this class is completely wrong. So that was fun to know that you have about 7 handouts that are out on the internet that are wrong. But I learned, and I'll fix it and tell you about it on Thursday. This is a hard class. I'm just gonna level with you. This is a really hard class because each of these specialty models could be its own class. And I'm trying to give you a survey of all of them, which requires learning each of them well enough to teach, but not so well that I don't screw it up. And I screw it up sometimes. Anywho, other questions?
Sorry.
Go ahead.
Okay.
I've had my time. Go ahead.
All right,
This
Nikki?
is less of a question and more of a noticing in Stata.
Okay, go for it.
So when we're doing logits, the command to get odds ratios, you have to do the option of OR.
Mhm.
If you run logistic command, that automatically gives you odds ratios, and then when you do lintom, you don't have to specify odds ratios, it gives it to you automatically in odds ratios.
Excellent. So is that for binary only, logistic?
I think so.
Okay, that is helpful to know.
Just in noticing.
Yeah, no,
I
that's
couldn't figure out why my code was wrong, and then I was like, oh, that's because I ran logistic instead of logits.
Nikki, quick question. Do you mean that in the sense of if you use lincom after using logistic? Or okay, got it.
Yeah, because I was like, oh, I normally run logistic to get odds ratios. Is it the same thing as running logit with the option of odds ratios? And it was. And then I left that logistic command, so when I did the LinCom on like the first section, it already reported to me in odds ratios. And then when I got to the second section, I didn't repeat the logistic command, and I was in logits, and I'm like, why did this first section give me the right answer, and the second give me the wrong answer? And it was because of the logistic command.
Okay, so just to make sure I'm following, if you do logistic to predict a binary outcome, it gives you logits and odds ratios at the same time?
No, it just gives you odds ratios.
Oh, it just
But
gives
if
you
you
odds
follow
ratios.
up with the LinCom, you don't have to specify odds ratios at the end. It automatically gives it to you.
So
Yeah.
logistic is sort of oriented in odds ratios as its base, as opposed to
Yep.
being oriented in logits and then a comma for the option to make it an odds ratio.
Yep.
Okay, gotcha. Yeah, in Stata, there's more than one way to do the same model, and we'll see this with the counts. For instance, Stata has a GLM package, and it has separate packages for like each type of count, and they each give you something different that the other one doesn't. So you end up having to run the same model like 2 different ways to get all the pieces that you want, and I don't know why that is, but it sounds like that's yet another instance of it giving you some things and not others. So that's good to know. Thank you. Yes, tips and tricks and things you figure out by trial and error are always welcome in every program. All right, Nathan, did you have a question or a comment too?
Yeah, I was just to re-clarify, like, how do you interpret odds ratio differences between slope coefficients?
Yes, I got a couple emails about that one. So one of the questions on the homework asked you to compare the slopes describing the effect of number of publications and number of conference presentations. And that type of question to me makes sense because they're both in the same units. Like if you only have so much time, should you put your effort into getting one more publication or one more conference presentation? That's sort of the idea. And the way that I simulated the data was such that publications are worth more, which is, duh, right? That's the world we live in, for better or worse. So in order to compare the difference in those slopes, there's an order of operations that has to be taken in order for it to be correct. You can take the difference in the slopes in logits, and then that is analogous to an interaction term, actually, because it's a difference of a slope. And then you can take that slope difference in logits and convert that slope difference to an odds ratio. That's the right way to solve the problem. If you found the odds ratios for each and then subtracted one from the other, you would not get to the same place.
Okay.
Yeah, so generally speaking, anytime that you want to do something resembling a hypothesis test or a comparison, so of one slope versus the other, or a slope against 0, or something like that, do it in logits and then work your way back to odds from the result. Don't do it in odds to start with. All right, rumors. I got 2 rumors here. They're awfully quiet. Either of you have questions about anything? You just chilling?
Yeah, I have one, but it's not related with the homework.
Doesn't have to be about homework. We're just talking about life today.
With one of the slides, it is about how to interpret the log likelihood sum, because one of the slides said that the log likelihood bigger is better, and
Yes.
-2 log likelihood smaller is better.
That is correct.
If I'm not wrong, it is 18.
Let me pull up that slide and share my screen so that we're all looking at the same thing.
Yeah, exactly.
Yep, 1 second
Last
here.
sentence, it says the LL bigger is better and -2 LL smaller is better.
Yes.
So, but I cannot understand now, because when we take -2 log likelihood, to me it is like to have the same number multiplied by 2. So
-2.
-2, but I think that in both cases, bigger is better. Why, when we take -2 log likelihood, smaller is better? That's my question.
So did you all hear the question? So why is it that what better means flips? So log likelihood is the sum across observations of the height of the data given the model. And you want the data to be as tall as possible. So bigger is better in that metric. If you take that number and multiply by -2, you're changing the direction of what up versus down means. So it becomes opposite because you're multiplying by -2 as opposed to just 2.
Yeah, but the thing is, for example, if my likelihood it is minus 500, and I have another version of the model which the likelihood it is minus 600. If I take those sum of likelihoods multiplied by minus 2, I will get 1000 and 1200. In that case, I would say that the better model it is the which one that has minus 600, for example, which is equal to 1200, and that model has a better or a bigger minus 2 log likelihood.
I didn't quite follow your numbers in that example, but I can pull up the formula by which.
Yeah, please.
Yeah, that's on the next slide here. So this is slide 19. It's too far. So you would, the result is the same if you do the straight difference of minus 2 log likelihood as a unit, or if you do the likelihood from the model that has fewer parameters minus the log likelihood from the model with more, and then multiply the result by minus 2. Either one gets you to the same place.
Okay.
And so because you're eventually going to have to multiply the difference by minus 2, the programs that report it this way are just trying to do you a favor, because then you can take the straight difference and it's easier to eyeball it.
Yeah, I think it is confusing.
It is
right
confusing.
Now. I can understand the reasoning, but when I try to apply those ideas, it's difficult. Can you go back to the previous slide?
Yes.
Because for me at least, if I have a likelihood, for bigger is better, but in the sense of more negative values are better. That's
true? No, less negative.
Ah, okay.
Yeah, it's not absolute value. It's still signed.
Okay, yeah.
Yeah, so it's the reason that it's usually a negative value is because you're in logs.
Uh-huh.
And that, to make matters even more confusing, this procedure of calculating minus 2 times the difference in log likelihood is called a likelihood ratio test, but there's not actually a ratio here.
Yeah.
If you had likelihood, not log likelihood, but likelihood, then it is the likelihood of the model that has fewer parameters divided by the likelihood of the model that has more. But because if you take a log, then you can do subtraction instead of division, then it becomes a difference like this.
Nice, yeah, now I get it, thank you.
So, yeah, it is confusing. It's just that you have to know which way is up, you have to figure out if your software is giving you this number or this number. And once you figure that out, then you'll know what to do. I can tell you that M+, for instance, everything is in log likelihood. In Stata, at least as far as I've seen, everything is in log likelihood. In SAS, it depends, but most of the time it's minus 2 log likelihood. And in R, all bets are off. It's whoever wrote the package and what they decided was important.
Okay.
But you can always get from one to the other. Had another question, are there instances where using BIC is better than AIC? Yes, BIC has more of a penalty for complexity. So the model has to get more better if you add a bunch of stuff to it. Which one is the right answer is a whole lot of opinion, and there's 8,000 versions of these that have been created for that purpose. So I don't have an opinion on that. And yes, there are instances in which they will disagree with each other.
I mean, that makes sense because, like, when I think of, taking the log of something to control for really extreme values, so, like, there's a ton of, like, really high stuff, then it would kind of put it at a more reasonable scale, I guess. Is that kind of, like, what it's getting at? Like, there's a lot of added parameters, and it brings it down to a more manageable scale.
I'm not sure if, to me, you sounded like you're talking about a log transform. But both AIC and BIC start with minus 2 log likelihood as their root. And so these are in a smaller is better metric, and then there's a different correction for number of parameters. One is just 2 times parameters, the other is log of sample size, and that differs across programs once you get to multi-level models. And then there's others that throw in corrections for small sample size and other kinds of stuff in here too. Yeah. So it's there's a whole thing.
That makes sense. Is there a reason why -2, like, where did that come from?
Because then the difference follows a chi-square distribution.
Oh, okay.
That's why. Sort of. Approximately a chi-square distribution, I would say, is true. Yep, that's why. Other questions? What's the meaning of life? It's 42. That's a Hitchhiker's Guide to the Galaxy reference right there. Do you want to jump back into proportional odds models then? Why not, right? We're all here. So reminding us briefly how models for ordinal data work, which is what we're talking about at the moment, and then we'll get into nominal. Back to this is slide 26, just to pop this in for a review. The whole idea of ordinal models is that they're based on a cumulative link function, meaning that all possible answer categories get used in each of the binary submodels. So if I have 4 answer categories, I would have 3 submodels that would look like this, where the binary part is the red versus green. So 0 versus 1, 2, 3 is the first binary submodel, 0, 1 versus 2, 3, 0, 1, 2 versus 3. And then from here, you have to figure out if what is being given to you as some kind of intercept-like parameter is referring to the logit or probit of the probability of the green part, the higher of the 2 possibilities, or the probability of the red part. And if what it's giving you is green, then you can think of it as an intercept. If what it's giving you is the red, then it's a threshold. So empty model is always my first step to try and figure out which way it's going. And then you have to figure out which way the slopes are going, because sometimes the slopes match the intercepts or the thresholds, and sometimes they don't. So what you can do is put in a binary predictor where you can easily check the mean for your outcome of one group versus the other and see whether it's going up or down, and that will answer your question. So a little bit of detective work needed to start with these models. So each of these then only indirectly tells you what the probability is of the middle categories. So the first submodel directly tells you what the probability of a 0 is, or it's going to be 1 minus that. The last one directly tells you what the probability of a 3 is, or it's going to be 1 minus that. But to get to the probability of a 1 or a 2, you have to subtract across the submodels. So for instance, to know what the probability of a 1 is, you'd have to compute what the probability of 1, 2, 3 is, and then subtract off the probability of 2 or 3, and then you're left with 1 as the unique part. So these models, I think, are less potentially useful if you care about each specific category as its own thing. Like if you're just wanting to think of this as like a regression and you want to do a regular old regression, but you know it's ordinal and then you just kind of want to do it fine, but you're thinking of it as more is better, then this is the type of approach that maps onto that. If you care about what predicts somebody answering 1 instead of 0, or 2 instead of 1, or 3 instead of 2, this is not the model for you. It doesn't do that. Instead, you'd want to do an adjacent category logit or a nominal model. So that's where we'll end up with in this example today. All right, any questions on submodels before we jump back in? Cool, all right. So I am in example 2B here. We started this last time, and playing with the same data of predicting the logit in this example of somebody applying to graduate school, where 0 is no, 1 is and 2 is very likely. And last time we looked at the frequency of that outcome for each category so that we have our answer key with respect to what the model is predicting. Then we looked at an empty model to verify that. So an empty model has no predictors. It should return either intercepts or thresholds, depending on your software. And in this case, the 2 parameters that we get back are the intercept of a response greater than 1, so meaning a 2 instead of a 0 or a 1, and the intercept of a response greater than 0, meaning a 1 or a 2. So we have our minus 2 log likelihood value as our baseline for comparison, our 2 intercepts. SAS does the I-link probabilities, so will Stata via margins. OLogit gives thresholds, which is why I'm not using that one, and instead I'm going to use GoLogit 2. and the RVGLAM package I'm using for this because it has an option to take away proportional odds as well. Okay, then we did a main effects model and highlighting with respect to the notation. The standard version of this model, which is known as proportional odds or ordinal regression, assumes that the slopes are the same across the binary submodels. So even though each submodel gets its own intercept or threshold that represents kind of the jumping off point for the reference person, from there, the effects of the predictors are the same, regardless of what you're actually predicting. So in Glimix, it's link equals C logit. Do you remember what C stands for? Did this last time?
Categorical?
Close. Categorical was a guess? Not quite. C. What's the C stand for in these models? Cumulative. Ding, ding, ding. Yep. And dist equals mult is multinomial. So then in this case, to your question, where'd you go? There you are, Cassandra. Your box moved to a different point in my view. Sorry, I was looking for you. This is why I would use fake people to not do all of this. Unfortunately, in this model, I don't have a choice because in order to create a prediction, it would have to create a prediction given a response of 0, 1, or 2, and my fake people don't have that. So I ended up having to do all of this anyway for this particular example. So we looked at, I think, the output for this last time. So here are my two intercepts. Do you remember what they tell me? First off, big question, what scale am I in? Am I in logits, odds, or probabilities? I'm in logits. Give me a synonym for logits.
Log of the odds.
Log
The
odds.
probability.
Yeah. Log odds is what a lot of people will call this. So I tend to say logit, but log odd is equally correct. And if I have this intercept parameter of minus 2.5 logits, what is that telling me?
That the probability of 2 instead of a 0 or 1, it is between 0 or 0.05.
Yeah, if you can convert logits to probabilities in your head, good for you. This is the logit of a response of 2 instead of 0 or 1 for my reference person. So when all my predictors are 0. And this one is the logit of a response of 1 or 2 instead of 0 for my reference person when all these predictors are 0. And so from there, this is the increase in the log odds for a 1 unit difference in each predictor. And it looks like GPA matters a little bit. Whether your parents went to grad school matters, and whether you went to private school does not matter. And here are the associated odds ratios that go with each of those slopes. And then here are the predicted probabilities for various types of people to try and illustrate how the model works. And last but not least, this thing right here. So I asked SAS to do an inverse link on the slope, and it happily did so, even though that makes 0 sense. So if you have a slope that's in logits, you cannot convert that slope into probabilities. It does not work. You can convert the slope into an odds ratio, but you cannot convert it into a probability. And so this model then is illustrated by the plot on the left here. I have just the x-axis is just the 12 people. The point I wanted to make is that the lines are exactly parallel. The predictions differ only in their intercept because the model assumes constant slopes across submodels. And this is me doing the work in SAS to create predicted probabilities for each that are automatically given by margins in Stata. So predict XB gives you the predictions in logits. If you leave that off in Stata, it gives you the predictions in probabilities of each of the categories. So here are the results of those margins that do it directly for me. Here are the odds ratios that I got by rerunning the same code and adding the comma OR option. And then we were, I think, leaving off with R maybe. We got to this part. So in this case, I'm using, which one am I using for this? I'm using VGLM. That's within the VGAM package. And it does give you -2 log likelihood and likelihood directly as part of the output. I then added commands to get AIC and BIC and to get odds ratios. The odds ratios do match exactly because they're just exponentiated logit slopes, but the confidence intervals that it does in R are some kind of resampling based thing, so they don't match the ones in the other programs. So that will be something I do not ask. And then finally, the chi-square that we get for the wald test of the 3 slopes does not match the other programs either, and I still don't know why, so I'm not going to ask any of those on your next homework assignment. I'll figure it out someday, but that day is not today. All right. So I think this is where we left off, right? And I told you to come back for the exciting conclusion of non-proportional odds. So it turns out that finding software to fit these models is non-trivial. That's why I'm using the VGLM package in R, because it was the only one I found that would do this. And likewise in SAS, I have to switch packages away from Glimix because it doesn't do it either. So here's the new model that we're starting with. This is page 10 of example 2B. And what's the difference in my equation relative to previous?
The slopes between the submodels now are
Yeah,
different.
yeah. I'm using a different I picked up the second subscript to say which submodel the slope is for. So again, there's multiple ways to probably notate this. This way works as long as you have fewer than 9 slopes to be added, but it's my way of conveying a coordinate system of which predictor variable and which submodel. So this is the concept of what we're going to do. The execution is a little bit more tricky. Okay, so we're letting each submodel have its own slope. In SAS, it's proc logistic to do this. Glimix does not have this capability. Logistic is a built-in procedure that only does categorical data, so it only has a multinomial distribution, but you do have to tell it which link you want, and so it's C-logit for the same before, cumulative logit. There's an option called Unequal Slopes that you can add that allows you to fit this non-proportional odds model. So the predictors then that go in they go in exactly the same way. You still only list them once, but then in several other spots here, you can ask it to compare the slopes across the submodels. So I have these are kind of like estimate statements, but they're an older version called a test statement. I think in newer versions of SAS, they added estimates to logistic, but I wanted to make sure that it was backwards compatible based on whatever version you might be using. So this first part in the code is a label that's going to show up on your output. Normally labels are in quotes and they turn purple, but this one is not. And then the test command here is the analog to contrast. So I am listing all 6 slopes that are in my model because I have 3 predictor variables and 2 submodels, creating 6 slopes total, and setting each of them to 0, separated by a comma to create the numerator degrees of freedom. So this is the analog to the F-test or chi-square test for the model R-square. Now I've got 6 slopes in it instead of 3. Likewise, the underscore here, _1 and _2, that's how you tell SAS which submodel you're talking about. And those specific values are tied to what they are in your data set. So I had to know to write this code that SAS was going to refer to my submodel as 2 versus 1 here, because I'm 0, 1, 2 for my choices. And so, for instance, this line right here is asking if the slope for GPA differs across the submodel, predicting a response greater than 1, or excuse me, a response greater than 1, which would be a 2, or a response greater than 0, which would be a 1 or a 2. So I wrote 3 different statements to test the assumption of proportional odds, as well as an omnibus 3 put it together test for the overall model. So this is where I ran into trouble by having value labels before, because then the value labels have to get attached to these submodel things, and it makes it more challenging and error prone. So I'll show you how to do this in each of the packages in turn. They're all getting at the same idea though, where we have a separate slope for each submodel now allowed, and we can ask if they're the same or not. Okay, so SAS users, any questions on this? No? Okay, so what we get back then is slightly different output than what we're used to seeing in terms of the order. So it gives me AIC, and it gives me -2 log likelihood, and it does it for the empty model as well as my current model, even though I only fitted the current model. And then here are 3 different types of tests for your model. So this is given for you in this routine. It's not given for you in Glimix. And so these are the 3 possibilities of what R could have been giving me by the walled test chi-square that I thought was a walled test. It could have been a score test, it could have been a likelihood ratio test instead, and it matches none of these. So I don't know what R is doing, or what it was supposed to be doing for that one. Here are the parameter estimates. So note that I've got estimate and standard error, and then this column right here is different than what we're used to seeing. This is a chi-square. What would this column normally be? Not F. It's single degree of freedom tests in this table. Different letter. Did I hear it? T. It would be normally be T, except that we're not using denominator degrees of freedom. So what does T become if you have an infinite sample size? Close. Do we need to review this? Oh, we got one answer. It's Z. It's Z. Yeah. Yeah. So let me pull up a slide on this. This is one of those things that I figured out much later than I should have, so I try to make a point of it now. Here we go. Okay, this is slide 18 in lecture 2. This little table here tells you what your test statistic is. So if you're testing one slope at a time and you're doing so without denominator degrees of freedom, estimate over standard error is treated as a Z. If you're testing one slope at a time and you are using denominator degrees of freedom, estimate over standard error is treated as a T. Question?
Is that the central limit theorem that like T distributions become more like normal distributions if there's tons and tons of sample size?
To my knowledge, that's not the central limit theorem, but it could be something else.
Okay.
T eventually becomes Z, yes.
Okay.
The point at which that happens, I don't know. It's not 30. I know that based on, like, that rule that I was taught is incorrect. I have another slide on that from my other class I can show you, but it doesn't work out to be 30. So Z, then, is the same thing as chi-square if you square it. And T squared is F. So that is to say, this column right here is Z squared instead of Z for reasons that I don't know. But I know I can get back to Z if I wanted it. So in homework, I try to specify like what test statistic I want, because there are 4 possibilities. And you can go back and forth to some extent, but not always. So if you're testing more than one slope at a time, though, that's when it has to be either chi-square or F, because you would want, because they're in squared units so that the sloped directions don't cancel out. So you can have a test of a positive slope combined with a test of a negative slope, and they do it in squared units so that you don't end up with them canceling out because of the direction. So when we test like the model R square based on multiple slopes, it's a chi-square. If it's degrees of freedom involved, it's an F, like we had in the golf example or linear model land. Okay. So these are our slopes let's eyeball these. So the effective GPA, I got two slopes here. The slope of 0.7 is predicting what? The first line that I've highlighted.
I
Wanna
would say that it is the difference in the log of the odds for the probability of having a 2 instead of 0 or 1, holding or adjusting for the other variables.
Yes, so it is the difference in the log odds of answering a 2 instead of a 0 or 1 per unit
Yeah.
GPA, right? So we got to get the units on there.
Yes.
So the log odds increase by 0.7 per unit GPA when we're predicting an answer of 2 instead of 0 or 1. And then for this one, same story, different submodel. So the log odds of answering 0 or the log odds of answering 1 or 2 increase by 0.59 per unit higher GPA. So if I'm just going to stare at these numbers, they're both on the same scale. They're both a change in a logit for a 1 unit change in GPA. It looks like there's a bigger effect of GPA in saying, yes, I'm definitely going to go to grad school, than in saying, maybe or yes, I'll go to grad school. But the question is, are those two slopes really different or not? Their standard errors are quite different. Can you guess why that might be?
Multicollinearity?
Multicollinearity would potentially be a reason why the standard errors are high for predictors in a model that has more predictors than fewer predictors, but it shouldn't affect this model.
Okay.
What else goes into standard error? Scale does, so like the variance of the predictor and then the unique variance of the predictor, which is what collinearity issues are about, but there's one more important thing. Sample size, yeah. What percent of my sample said 2? 10%. 10%. So the standard error for this submodel is higher because there's fewer people contributing to the prediction of a 2. So it looks like GPA matters a little bit more just numerically if I'm predicting a 2 instead of a 1 or a 2. These two look like they're pretty much the same, although slightly more if I'm predicting a 1 or a 2 than a 2. And then these two are in opposite direction. Now, neither one of them is significant, but this type of result should give you pause. Meaning, I really don't want to lump slopes together if they're in opposite directions. So the log odds are lower if you went to private college for predicting, yes, I'm definitely going to go to grad school. But the log odds are higher for predicting maybe or yes than no. So we would want to determine for each of these variables whether 2 slopes are necessary, whether we could get by with the same slope for both, or whether we need that variable as a predictor at all. So far, it looks like we only need a couple of them based on just eyeballing the significance tests. So SAS directly gives us the slope for each submodel. I then did significance tests separately via those test statements to test the difference in the slopes. And those are in chi-square test statistics. And it looks like 2 of the 3 are not different. So the slope for GPA is not different across submodels. That's what this p-value of 0.08 is telling me. Likewise, the slope for whether your parent went to grad school appears to not be different across submodels. And then there's this one, a p of 0.0585. just barely not different. So each of these is contingent on how many other slopes are in the model. I might expect a different result if I had collapsed the other two into a single slope. And overall, there's no proportional odds violation of the whole model, even though it looks like 2 of them are fine and 1 is questionable. Now, wouldn't it be nice if I could get all of this at once without having to type so much? Wouldn't that be nice? Stata folks, this one's for you. The Go Logit 2 package anticipated this need. The option gamma provides you with direct tests of whether the slopes are different across submodels. 5 little letters. It's amazing. I went ahead and wrote it out because I wanted you to see how you would ask for it if that weren't given to you as an option. So the test statement here is just like the ones that you're used to seeing for lumping together slopes to get a walled test for the model, with the exception that which submodel it is the bracket part. And this is tied to how Stata labels things. Like in the output below, it labeled the submodel as a submodel for 0, meaning that it's predicting the logit of 1 or 2 instead of 0. And it labeled the second submodel as 1, which means that it's predicting the logit of, oh goodness, this one is, did I write it out? Yeah, this is the second one. So this is a logit of 2 instead of 0 or 1. Yep. So based on this output, I knew what to write here inside the brackets. And as one of you told me, who was that? Was that you, Kendall, that told me about CoF Legend in your email? Yes, I had seen that one before and forgotten about it. There is an option in Stata that you can add that is, I think, CoF Legend. I think it's something very close to that, where then it spits out like the internal names that Stata uses for different things. So if you're not sure how to refer to a parameter in these sorts of statements, then you can use this to figure that out. So I used that when I was doing SEM in Stata, but haven't done that since. So here are the 3 slope differences like I asked for in SAS, even though that's technically not necessary. And then here's a combined test of all 3. So then in the Go Logit output here, I get the results for each submodel separately. So it's the same information as provided by SAS, just in a different order. And I've highlighted the one that looks like it is different. And then here's the second piece where the gamma option, it says gammas are deviations from proportionality, meaning these are differences. So let me try and fit as much as I can on a screen so I can show what happens. Okay, question?
So is the difference between the 2 slopes, could that also be an interaction, classified as an interaction term?
No, because it's a difference in the slopes across submodels.
Oh, okay.
It's the same idea, though. A difference in slopes could result from a moderation addition or literally like 2 different sets of slopes for predicting the different pieces of the same outcome. So here's the submodel for 0, like 0.59, and so we'll do this one, and that one. There we go. Now I've got all the numbers on one page. So 0.59 is the slope of GPA in predicting a 1 or a 2 instead of a 0. 0.72 is the slope of GPA in predicting a 2 instead of a 0 or a 1. The gamma 2 parameterization gives you the difference in the slope. So it's how much more positive the GPA slope is in the second submodel than the first. So these are, as I've indicated out here, this is me trying to be nice and labeling what these actually are. These are differences. So under this parameterization, it tells you directly, in Z's, by the way, so note it's a Z-test statistic and then probability of a Z, tells you directly that the last one looks like it's almost different. And then it has the intercepts down here because they're always different. That's not a thing. Okay, how are we doing? Question?
Could you also use this, like if they do have differing slopes like this, would that be evidence that the scale is not interval?
I wouldn't say you could say that in this case,
Okay.
because you're already in a cumulative link metric, and the slopes are going to be nonlinear to begin with.
Okay.
I would say that you could, if you had a predictor that was an ordinal variable, you could ask whether the slope between each adjacent category was the same, and that would be a test of whether you could treat it as interval. But that's related to, but different than this, because this is an ordinal outcome, not an ordinal predictor. And then here's the rest of the stuff. So these are the extra tests that I asked for, and they are chi-squares, but their probability, their p-values directly match the ones from the z's, because z squared is chi-square if you're only testing one thing. All right, so I know there's relatively few Stata folks, but any questions from those folks? Probably more Stata folks than SAS folks, but SAS is what I use to make sure I know what I'm doing. So that one I have to keep in here. No, we're good? Okay, go Logit. Okay, our folks. So there are, let me make this a little bit smaller so we can see here. Here's the new thing, right there. Parallel equals false. That changes the overall model to be a non-proportional odds separate slopes for each submodel model. Everything else is the same. So then I wanted to go in and ask for the same pieces of information with respect to testing the slope differences. I had to figure out the order in which they were going to be listed in the output, though, before I could do that. So here's the R output, and it does it in the same order as SAS, where it goes by term, except that it's listing the first submodel, and so this is the probability. This one corresponds to the probability of a 1 or a 2 instead of a 0. This one corresponds to the probability of a 2 instead of a 0 or a 1. And then we get the slopes for each. So based on this ordering that it came up with, then I could write these GLHT statements to get the differences between the slopes. So you'll note the -1, 1 combo. So that one is for GPA. And then the next two down, -1, 1. This one's for parent. And then the last two is for private. So this form is how you get a difference between things. It works out to be one minus the other. And I always list the one that I want as the reference for the comparison first, and that gets the -1. If you switch the -1 and the 1, you would get the same significance, but it would be backwards in terms of the coefficient or the test statistic. And then lumping together the three tests of those terms for a joint test of proportional odds violation is this last part here. So I want to lump together that slope difference, and that slope difference, and get a degree of freedom 3 test. Okay, it's a lot of code there, but most of it you've seen before. Questions from our users on the coding part? So what I found happened in fitting these models is that this is the VGLM package. It's the only one that I found that does non-proportional odds. That's why I'm using it. There may be others, but this is the only one that I found that I could make work. And the standard errors for all of these things are just a little bit different than the other two packages. And so that translates into the walled test being a little bit different and each of these submodel tests being a little bit different. So because of that, you won't be doing these tests in your homework.
Yeah,
Question?
I have a question for the part of unit test of submodels. It is in that page. If you
Yep.
scroll down, yes.
This right here. Yep.
So in that part, Lisa, we have these differences for each slope between the submodels.
Yep.
So those differences in the estimates of the slopes, do we have to interpret them as in previous homeworks? Like, for example, this is more helpful, less helpful?
Yes, you will have to do that, because the signs match.
Yeah. And all of this, it is related to the probability of having a 1 in whatever we are trying to predict.
That's right.
Nice.
Yep. So like this number right here, this is a slope difference. So it's positive, meaning that the second slope in my comparison was more positive. But you can go up to the numbers here. So here's the numbers all put together again. The slope for submodel 2 is more positive by 0.12 than the slope for submodel 1. So more helpful, more better, like whatever my wording is for that time. It's a more positive slope means that there is a bigger change in the predicted logit. And this one right here, if I continue the pattern, that's a negative slope difference, but in order to interpret it, you have to know what the slopes are. So that negative coefficient for the difference, I would say, means the second slope is less positive, because they're both positive slopes. So not as helpful would be the corresponding words for that idea. Assuming you have an outcome in which more is better. And then the last one, this is the type of situation where my language breaks down, because you could say the second one is less positive but also more negative because it switches signs. So when I get to a position like this in life, I dump the less positive, more negative, less positive, whatever language, and I just say this one is positive and that one's negative, and they're different, p less than 0.05. In your homeworks, I try to make it so that you don't ever end up in that ambiguity. I try. But it looks like these two are not the same. P of 0.05, 2 in R. All right. So what I found in SAS and in Stata is that both of them have options within these procedures for letting it figure out what the optimal model is. So the code online has a demonstration of that, where it goes through and figures out which slopes need to be different, and also which ones need to be included at all. So it's kind of like a stepwise regression automation kind of thing, which generally speaking I'm not a fan of, but in this instance I think it's helpful for figuring out which slopes are different, because the results would change based on which ones are currently different and which ones are not. And both of them converged onto the same answer, where only the last slope needs to be different. So it turns out that once you get rid of these other two differences, the last one is significant at p less than 0.05. So this is the model that we end up with. So it is possible then to set up a model in which only some of the slopes differ across submodels. I learned how to do that too. So we've got, in SAS, there's an option after unequal slopes. If you just type that, they're all unequal across submodels. If you only want certain ones to differ across submodels, then you list the ones you want to differ. And so then the other two are constrained equal across submodels, back to what we started with, and then this one gets to differ across submodels. So even though the difference between them is significant, neither is significant in its submodel. So one could argue you don't need this variable at all. And they do differ at p of 0.03 now, once you take out the other two terms. In Stata, it's this NPL, and then you put the predictor in there that you want to be allowed to differ across submodels. Not proportional something, and I'm not sure what the L stands for. I don't remember. So then we get the, where'd it go? Two different slopes for the effective private, and then the gamma output down below gives you the test of their difference. There's your p of 0.03. And last but not least, in R, parallel equals false squiggle variable name. I had a student in the other class ask last week why we had to put squiggle in here. And I said, because equal was already taken. That's why. This is a tilde, as far as I know, right? I know it. I learned that in Spanish. Are there other languages that have tilde? Yeah, that's a common one. Okay. It's the thing above the shift key. So then I listed that variable as the one that I want to have separate slopes. And I can still test whether or not those slopes are different within the same linear combination procedure. And there we have it. All right, how are we doing?
I'm sorry, did I enter a class hours now?
Yeah, and this class is over at 1:45, but you're welcome to hang out with us.
Sorry.
It's fine, I don't care. The more the merrier. I know I've got 4 people in front of me and 15 people on Zoom, so it's all good. Plenty of room for everyone. So are any of you thinking to yourselves, how in the hell did she ever figure out all this stuff? Because it's non-trivial. Let me show you how I did it. I wrote out my own model in SAS. So there is a command, I think it's nlin or something like that in Stata, and I'm quite certain there's a way to do this in R that I've never played with. But let me show you briefly the idea of proc nl mixed, where in SAS you can make up your own model and estimate it if you know how. So I wrote out various versions of this that I thought, well, what if I set up the model this way, what would I get back? And then I played with it until I got the results to match across the 3 packages, and then I knew what it was doing. So NL mixed allows you to write out any kind of model you want and define the parameters. So I use this for anything that's a truly nonlinear model, as well as IRT models you can fit in here. So like explanatory item response models can be done in here. I have examples of NL mixed for various things, so if you're interested, I can send them to you. But the idea is that you define the parameters and give them start values. So these are my 2 intercepts and my 2 sets of slopes. You then write out the linear predictor. So I'm building y1 as my submodel predicting a response of greater than 1, and y0 for my submodel predicting a response greater than 0. Here's my intercept. Here's my slope times the variable GPA. Here's another slope times the other variable, slope times variable. This part right here comes from, let me find the slide. The likelihood function is defined by how the model recreates the predicted probabilities for each subgroup, each response, right here. This is slide 26. So how the model tells me what the probability is of each category, right there. I wrote that out right here, so it's making my own custom likelihood function. And then I tell it I want the log of the likelihood, and here's my outcome variable. So any model that you read about that there's not a package for, you can do in this type of setup. So I use this to figure out what other programs are doing a lot of the time, because I know that if I set it up, I should know how to interpret my results. And so this is where I started in trying to figure out all this stuff. All right, ta-da. So you're not going to have to do that, but I wanted to just point that out as a resource for you. Yes, sir.
So with the ordinal regression models, that's, you said, was graded response in IRT?
Yes, it is.
And then the nominal is partial credit?
Nope. Adjacent category is partial credit.
Adjacent category.
Yep. So the translation into the world of IRT is, let me see here. So the one that we're doing right now, proportional odds, is graded response models. And to the best of my knowledge, there is no non-proportional odds version, although there could be. Like you could make it yourself using the NL mixed or some other way of estimating it. But the graded response model says the slope for item discrimination is the same across submodels, in the same way that these models have the same slope across submodels. The other two that you will see, Adjacent category logit divides up the binary submodels using each pair of adjacent responses. This is a partial credit model in IRT. If you allow a different slope across items, it's a generalized partial credit model because the original partial credit was a Roche model where the slope is the same across items. This is the one that I think makes the most sense, but for whatever reason, it never gets used, and it's hard to find. And then nominal is the last one that I have an example of, which looks like we won't get through today, where you designate one of the outcome categories as the reference, and then it's like you dummy code your outcome. And that's how the submodels are created. So nominal is made for unordered data, but you could use it for ordered data if you really care about each of the categories. All right. Other questions?
What would you use for polygamous?
Well, the polygamous, that word means categorical. So it would depend on whether it's ordinal or maybe ordered or not ordered.
Okay.
Yep.
So this would all be like umbrella polygamous.
Yep.
Okay.
Polygamous means not binary, as near as I can tell. It means categorical. Yeah, isn't it funny how each field has to invent their own words for the same thing? Like rediscovering the wheel.
We were yesterday in IRT. We were talking about there's someone that came out with it's supposed to be an update to like Lord's theories, and it ended up being like all the same stuff that Lord had said.
Mm-hmm.
I mean,
Yeah.
I'm simplifying that maybe a little bit too much, but
Yeah, so polygamous means categorical. The next models that we are not going to get to today, I've just made that executive decision here. We'll end a couple of minutes early. Nominal are also known as multinomial regression, but that's a bad word because multinomial is the distribution that's used in all of these models. So to me, that's not a helpful name. But this last one here that I'm staring at, what I call nominal, is also known as baseline category logit, generalized logit, unordered categories is the general idea here. And in IRT, this is called nominal too. There's another way to set up a nominal model in IRT, but that one gives me a huge headache, and I didn't have the strength to do it in this class. So just know, I got to draw the line somewhere, right? So this is one we're doing next time, where given that I have this 3-category outcome of 0, 1, 2, I decided that I would make 1 the reference category. And so we can predict the logit of answering a 2 instead of 1, or the logit of answering a 0 instead of 1. So then it works out to be the same as adjacent category logit. Cool. But that's next time. And I will let you know when more handouts are ready for Thursday on counts, which is our next unit after this one.
Okay.
Question?
Yes, Lisa, but it is related to the next content because I was reading about Poisson regression and count.
Yep, Poisson is
regression,
coming
and
next. Yep.
There is something that I cannot understand, but it is useful, I think. What is an offset?
Oh, an offset. Yes. An offset is a parameter that you add to your model where you force the slope of it to be a known constant.
Okay.
It is used in count data to correct for differences in number possible. Like if I was collecting an outcome, like number of fits that Huey threw this week because I took his Nintendo away, and you wanted to correct for like the amount of time I spent watching him this week as opposed to last week, an offset would basically be like a denominator that corrects for the total amount of time, and that way it's a rate that you're predicting and not a count.
Yeah, perfect.
That's what an offset is.
Yeah, thank you.
Yep. More of that coming next time. So. Any other questions before we wrap up?
partial credit models, that so it would be like predicting ability based on like how many points you earned.
Partial
total.
credit is that.
Okay, so like it'd be looking at the ability of someone who got a 3 out of 3 versus a 2 out of 3.
Not necessarily. A partial credit IRT model is designed to look at the conditional probability of one of two possible categories. So
Okay.
given that you answered 0 or 1, what's the logit you answered 1 instead of 0? If you want to talk about getting more than one like set of points for a problem, that's like sort of what partial credit like we think of as a layperson, but that's not a model in the IRT sense.
That makes sense.
Yeah. All right. Other questions? All right. Well, it's garbage day. That means I don't say have a good weekend, even though it totally feels like a Thursday already. But no, that means I say I'll see you Thursday. Thanks for being here. Let me know if you need anything. I'll let you know when you have something else that you need to do. But right now you have nothing to do. So hooray! All right. Bye, folks.